Does Ronaldo's knuckleball free kick break physics? It can rise, dip, and suddenly move sideways, even when the ball appears to have almost no spin. But the stranger the motion looks, the more precisely physics can explain it. If Ronaldo is no longer touching the ball, what force can still push it sideways? Gravity acts downward. Air resistance usually slows the ball along its path, and the Magnus effect normally needs spin. A knuckleball removes most of that spin, yet the sideways movement can become less predictable. Suppose the ball leaves the foot at 30 meters per second and travels 25 meters. Time equals distance divided by speed. 25 divided by 30 gives about 0.83 seconds of flight. That is less than 1 second for the ball to change direction, and less than 1 second for the goalkeeper to understand it. A normal curling free kick rotates enough to create a steady pressure difference. A knuckleball rotates so slowly that the same panel and seam can face the airflow for much of the journey. Instead of producing one smooth curve, the ball keeps presenting an uneven surface to the air. Air separates from the back of the ball and forms a turbulent wake. If that wake stays centered, the pressures on the left and right sides nearly balance. But if the wake shifts to one side, the pressure becomes unequal. The ball is pushed sideways. Acceleration equals force divided by mass. A football has a mass of about 0.43 kilograms. If the unstable wake creates a sideways force of only 1 newton, 1 divided by 0.43 gives about 2.3 meters per second squared of lateral acceleration. Now turn acceleration into movement. Sideways displacement equals 1/2 times acceleration times time squared. 1/2 times 2.3 times 0.83 squared gives roughly 0.8 meters. The real force keeps changing, so the actual path will not be one smooth curve. But the calculation proves that a small aerodynamic imbalance can move the ball by tens of centimeters before it reaches the goal. That is enough to defeat a goalkeeper. He has already committed his body toward the predicted path. The ball does not need to cross the entire goal. It only needs to move farther than he can correct. Why does the movement look sudden? Because the force itself is unstable. The wake can move left. We can then move right. Each change alters the lateral acceleration. The path becomes a sequence of small corrections instead of one permanent bend. Speed makes the effect stronger. Aerodynamic force grows roughly with speed squared. If speed rises from 25 to 30 meters per second, the force scale changes by 30 squared divided by 25 squared. That equals 1.44. A 20% increase in speed can produce about a 44% increase in force if the other conditions remain similar. The flow regime matters too. Reynolds number equals air density times ball speed times ball diameter divided by air viscosity. For a fast football, the airflow becomes highly sensitive to seams, surface texture, and where the air separates. Tiny changes in orientation can create much larger changes in the wake. This is why the knuckleball is not magic and does not violate physics. It is extremely sensitive to its starting conditions. Ronaldo controls the launch speed, contact point, angle, and very low spin. After release, the airflow amplifies tiny surface differences into visible motion. The goalkeeper faces a prediction problem. If the ball followed one smooth curve, he could estimate its future position. But when the sideways force changes during flight, that prediction keeps moving. By the time the new path becomes visible, the remaining reaction window may be only a few tenths of a second. The deciding condition is simple. If the ball's late sideways displacement is greater than the goalkeeper's remaining correction distance, the free kick wins. The ball does not break physics. It breaks the goalkeeper's prediction by obeying unstable physics perfectly.